So here is the term sigma SB. So it's a rather complicated equation, and in this particular case we have a result shown here. And then down at the bottom, if you have the checkbox checked, you can get these other intermediate results for the exchanger in the tabular format that you see here. Okay. So if you run this, you can see the terms for the membrane shell stress and the shell bending stress sigma SB. And these are the values that are going to be different, and consequently, since the total stress includes the bending stress and the membrane stress, the values in this column will be different. Okay, so that is the one of the most important of the UHX updates and the code updates. The next thing that we have is a change in, or an addition, I should say, to UG37 subparagraph H, which involves split reinforcing pads. Basically, when reinforcing pads are constructed, in many cases they're actually split into more than one piece, put back on the vessel, and re-welded. Okay. There is an area calculation term in area of replacement called A5, which is the area in the reinforcing pad. And if your pad doesn't meet the guidelines for full penetration or where the weld is located, then you take a slight penalty of 75% on the area, and I can show you that real quickly on a sample nozzle calculation. So, for example, if I just double-click on this particular nozzle, right up here in the pad properties, for those of you that are familiar with the program, you'll see a new checkbox right here. It says, for 8-1 split pads, reduce area 5 by 75%. Okay, so again, if your pad doesn't meet the requirements, then you need to check the box, and you'll notice down here on area 5, right here we have a current value of 0.888 square inches in this case. And if I check the box right here, notice that I have my 75% reduction. Okay. And if I want to look at a more detailed calculation, I can simply press the calculator button and come down, and also TV Elite will print out a note right here telling you that area 5 has been reduced by 75%. So that's quite simple. Okay, but it is important for you to read that code paragraph because it may help you to avoid having to take that penalty for the area. Okay, our next code change right here was the thick cylinder equations. Okay, so what I'm going to do is I'm going to open up a model right here that I've already created. Okay, it's called thick cylinder. And what this model is, as you can see here, it's a small diameter, high pressure model with a very thick cylinder. Okay, so to show you this equation, I have a couple of different choices of what I can do. I can come over here to the nozzle dialog, run the calculation, and I can show you the equation right here that appears in Appendix 1-2A1. And again, for those of you that have seen these equations before, you'll notice that this is actually the one that you will find in ASME Section 8 Division 2. Okay? Okay, another way I could see that, of course, is to actually just simply analyze the model. Okay, it's going to show me some of the warnings there. And on my results, I can have a look at the, again, at the equations, and here's the Newthig cylinder equations. And of course, also to go along with those equations, we have the back calculation of the MAWP and the stress. Okay, so those are more code changes that actually bring this part of Division 1 more in line with what's in Division 2. Okay, next, Section 2, Part D updates. These are the updates to the ASME material databases. As you can see, over 100 materials were added or modified. One of my colleagues, Luis, worked very hard on adding a lot of materials that weren't present in the database, and also modified all of the other materials for updates in things like allowable stress, notes, and what have you. I should also mention that last year in 2009, all of the ASME databases were reorganized. We've added columns for a more flexible database structure that will take us into the future. Okay, so all in all, these are some of the mandatory changes required for code compliance. Okay. Okay, so next we're going to get into some of the new analysis capabilities. The first one that we have shown up here is a ligament efficiency calculator. Okay, and you can see right here that we've highlighted this is per Section 8 Division 1 paragraph UG 53. Okay, you'll also find a very similar paragraph in Division 2, which is in Section 4.10. To get to this calculator, you will notice a new button on the toolbar right here, and when you put your mouse over it, it will say Compute Ligament Efficiencies. Okay, and again, all this does is it's just simply a calculator that will allow you to do something that might not be very pleasant to do, on your calculator. So basically, what you do here is you choose the figure that you want from the ASME code, and then simply enter in the information. So, for example, if I wanted to know a simple arrangement like this, say a tube diameter of 1, or a hole diameter of 1, and a pitch of 1 1/4. As soon as I do that and then I tab to the next field, PVLE calculates an efficiency of this ligament in percent. So obviously you would divide this percentage by 100 to get the decimal equivalent, which is what you would use to potentially modify an allowable stress. So you can see back here we have other figures, UG 53.2, 0.3, 0.4, and to go along with figure UG 53.4, you can select the figure that you want to use that goes along with that, which is 53.5 or 6. Okay, so that's basically how the calculator works. It's pretty simple. Okay, so the next thing that we want to look at is the Koppen-Sayer method of analysis for expansion joints. This again was a feature that was added per user request. And to show you how this works, I'm going to go back to our UHX sample model. Okay, and again, notice that that in this sample we have an expansion joint right here. It's a thick type expansion joint. Okay, so I'll just double click, and it'll bring us back to our tabs of information for the exchanger data. Okay, and you can see right here that we have our expansion joint input, showing you the ID, the OD, and what I'm going to do is I'm going to set the option right here to analyze, and I'm going to change it from TEMA method to Cop-and-Sayer. Okay, and I should add that this Cop-and-Sayer method is certainly nothing new. It's been in the industry for many years, and it's basically been shown to be certainly a good alternative to other similar types of calculations. Okay, so I'll go ahead and change it right here, and what I need to do now is go ahead and run the model, and we can have a look at the output now. Okay, and what we'll do is we will scroll down to the calculations, and you can kind of see this is where they start right here. Okay. So we calculate our differential expansion, and then you can see right here, this is where the Cop-and-Sayer analysis method starts right here. So basically you calculate a number of dimensions, parameters, and then of course with all of the information, it finally leads up to a calculation of spring rate, which is needed for fixed tube sheet calculations per ASME and TEMA. And then finally, right here, we have our expansion joint stress summary table. Okay. So again, you would get something very similar, a similar sort of calculation running the Cop-and-Sayer method or running the TEMA method. So they're very similar in what they actually do. Okay, so that's how you choose the Cop-and-Sayer method for your analysis. So, in some cases, it may be good to see what one method gives you versus what another method does. Okay, our next point right here is the Division II saddle analysis. Instead of the Zik calculations, the Zik calculations have been around for a very long time, pioneered by Leonard Zik, and these calculations have proved extremely useful. Many other codes have taken these calculations and massaged them a bit and included them into their own codes, such as PD5500. You'll find a variant there, as well in some of the other international codes. So the folks that have worked on the Division II code have taken this analysis and made it a mandatory part of the Division II code book. Okay, and this was something that I felt was really good for us. Now there is, since it's an ASME code calculation, of course still optional, in Division I. If you have a better way of doing it, that's fine, but this is an accepted method. PV Elite will use the Division II method where it used to use the Zik analysis. So again, what we can do is have a look at those results. So simply I'll go back to the calculation that I just did, and we can have a look at the horizontal vessel analysis right here, and it will show you what the stress calculations are. Okay. Again, for those of you that are familiar with this calculation, you will see that the output is a little bit different than it was before. We have some of the input right here, and then again followed by the table of results. Okay, and you're all familiar with this. This is pretty much very similar to what it was before. Okay, and depending on the location of the saddles from the ends and some other parameters, of course, the results, what you get in this table, will vary somewhat. Okay, and then further down right here, you'll see that we print out a table of the K values. Okay, and it is interesting to note that one of the stress calculations is actually about 10 times less than it was in the traditional Zik analysis because of this K factor for welded vessels. So, and generally, that's our assumption right here, is that when these horizontal vessels are constructed, that they're welded. Okay, so and again, you'll see all of the equations right here that you will find in Section 8, Division 2. Okay. So next, right here we also have the EN 13445 YouTube tube sheet analysis. Okay. Let's take a look at that. So I have a file, okay, that I've created. And again, it's similar to other heat exchangers that you can do. Let's just have a quick look at this right here in a cut view, and notice that we've got your basic run-of-the-mill YouTube tube sheet. Okay, again, then we can kind of zoom in on there, and notice that we don't draw all of the tubes. That makes for a lot of graphics processing overhead. But you can still certainly get the idea of what we've done here. So let's go ahead and analyze it. Okay, and then have a look at the results. And here we see our EN tube sheet analysis. As it turns out, this analysis is very, very similar to what you will find in ASME Part UHX. Okay, so the way the calculation performed is very, very similar. Okay, one difference in the method is for the tube sheet flanged extension thickness. You'll see here that it's quite a bit different than the equations that are currently up here in the ASME code. So the European code is a little bit different right there. Okay, so that is how that is another new feature that hopefully should help our overseas users do this calculation. And we will be following up in the year with the EN fixed tube sheet analysis, as well as the floating tube sheet analysis and floating head analysis. Okay, our next new feature right here is the lifting lug calculations. Okay, let's go ahead and look at a model that has lifting lugs right here, and I'm going to pull open this model right here, which is a Division 2 model that I made. And you can see here that we have a horizontal vessel, and what I did was I just simply created some lifting lugs. Now this, we can have perpendicular lugs for horizontal vessels, or we can have ear-type lugs on vertical vessels. So I'm going to show you all basically how this works right here. You simply click on your element, And then up at the top on the detail toolbar, you will see that there's an option to add lifting lugs. So you just invoke the dialog. It comes up, and then you fill the data in. So basically, it's just a matter of going down through all the inputs right here and typing in the data according to what you see in the figure. Okay. We can also have reinforcing pads. Okay. Slotted lugs. Okay, for flat types. And over here we can specify other data such as occasional load factor, impact factor, a force on the lug which causes weak axis bending stress, and also the sling angle from the horizontal. This was a small vessel, and since it was picked straight up and there was a platform installed on top, that's why I had my lug angle at 90 degrees. So this really is assuming that you had a spreader bar that was had a lift point directly above each lug. So let me go ahead and run this model for you, and we can have a look and see what actually happens here. Now you'll notice that we have a separate calculation for each lifting lug, the one on the left side and the one on the right side. So currently what we do is we have our input echo, and we have all of our computed results. And from there, we go through all of the basic calculations that you would normally have to go through when you're calculating stresses on weld groups and stresses in the lug itself. Okay. Now I should say that the horizontal vessel calculation is fairly simple since it just goes one way. Now notice also right here we have also performed a WRC 107 local stress evaluation. So you'll see that we have a radial load on the lug, okay, and we come through and we determine all of the stresses at the attachment and compare those with their allowables. Okay. Now for a vertical vessel, it works in a similar fashion, except that the angle of the vessel goes from horizontal to vertical as it's picked up, and that changes the loading on the lug as it goes through that rotation. So PV Elite will calculate stresses and loads at all of those different positions, and it picks out the worst values for you. Okay, next we have integrated WRC 297 analysis. Okay, this has been a requested analysis that we've had in CodeCalc for some time. Okay, and this is based on Welding Research Council Bulletin 297, and this is helpful in some cases because you know, some end users and clients, they specify that that's what they would like you to use. And it also handles a slightly wider range of diameter ratios than WRC 107 caters for. Okay, so basically to have a look at how that works, what we'll do is we'll just have a look at this vessel right here, this Division II horizontal vessel, and I'll bring up this nozzle with this piping extension on it right here. So I just double click there, okay, and you'll see it brings up the nozzle dialog. Now once that's over with, we have our local stress analysis tab up at the top right here. So we just click there, and from here you can see that we have a new option on the radio, as one of our radio buttons right here, and it's of course WRC 297. So once you click the 297 option, you will be allowed to type in the forces and moments that you have from your piping analysis, or the forces and moments that you have been given from a table or what have you to design from. Okay, so here we have, again, our radial load, and as well as all the other loads. So it's a total of 3 forces and 3 moments. Okay, so we type these in, and as we do that, you will notice that down here at the bottom of the screen, we have calculated some various stress ratios. Now, one of the additional things that 297 does is it calculates the stress in the nozzle wall. Okay. WRC 107 does not do that, so you get a little bit of extra information. And as it turns out, sometimes the nozzle may be actually stressed higher than the shell. So again, you see these ratios down here. And if you want to look at the calculation, again, you can press the calculator button, and we will show you the various results that come from the 297 calculation. Okay. So it's presented in a slightly different format than you're used to in 107, but we do the calculations for both, at the edge of the pad and at the edge of the nozzle. And then down at the bottom, we have summary tables, okay, that show you what the stress summations, okay. So again, many of you had asked for the stress summations for 297. So again, many thanks to my colleague Mandeep for going through for being persistent and getting this in there for all of our users. So that was a great thing. Now, again, with any engineering tool that you have, you've got to understand some of the limitations of these other various codes and bulletins and so forth. The WRC 297 method is only applicable for radial nozzles located in cylindrical shells. So basically, if you try to do a 297 in an ellipsoidal head or a flat head, PV Elite is not going to let you do that. Okay, so that's how that works. And again, if we wanted to look at that result in the output, when you run the nozzles and you get all of your reports, you will see that same report down here in the nozzle analysis, in this case for the drain. Okay. Okay, the next one that we have here on our list is variable layout angles for exterior attachment types, such as nozzles and platforms. So what do we mean by variable layout angles? Well, for those of you that have to enter in data from a drawing, different companies have different standards of how their drawings are detailed. Okay, so sometimes vertical vessel nozzles are oriented, say, to the north is the 0-degree mark, and you might go counterclockwise or clockwise. And so PV Elite's convention was originally, it was east and counterclockwise. Okay, so what we've done in this version of PV Elite is we have made that where it can be changed. Okay, so let's take a look and see how that works. Okay, so again, if we go back to PV Elite, okay, let me open up a model that I've created. called layout angles right here. And we will take a quick look and see how this is. Okay, so if we look at this nozzle right here, okay, notice that we have a layout angle of 270 degrees. So if we go back and look at the help screen for the layout angle, right here you'll notice that the default orientation for a vertical vessel is 0 degrees, pointing at the, going off to the right, with the angles positive in the counterclockwise direction. So 270 is down at the bottom. And if we look at that platform that we had, okay, notice its layout angle right here. Its start angle is 45, okay, and we have an end angle of 270 degrees. Okay, so the picture that PV Elite produces is currently according to the default orientation. Now, if you prefer or you have a different methodology, then what you can do is come into Tools and Configuration, okay, and change the default. Now, notice down here at the bottom of the job-specific setup parameters, we tell you what your current model orientation is. Okay, we have east counterclockwise. If we want to change that, we can come to the Set Default Values tab, okay, and we can change that. And you see here, we can go from any of these positions to any of these positions. So what I'm going to do is I'm going to go north and clockwise, and I'm going to make that my default. So when I start any models in the future, this is what the orientation is going to be. So when I say OK, PV Elite is going to prompt me. It's going to say, hey, the global directions and this model's directions are different. Would you like to update this model's settings with the defaults? And I'm going to say yes. Okay. Now before I press this next button, I want you to remember how this platform looks. Okay. This is just not a, we're changing direction. Okay. So we're actually, so the platform, its layout is actually going to change. So it's, this other dialog box is telling me, hey, if you have any platforms, you need to be sure and update their weights and areas. So let me go ahead and press OK. And now you can see how this has changed. Okay. Now, since I do need to change my platform's area, one simple way to do it is just to simply go to the platform dialog and tap around, and it will automatically change for you. Okay. If I come here to the list dialog, okay, I can do this for all of the platforms that I have in one shot. Now notice right here that the wind area and the weight are both grayed out. I can simply press the platform wind area button and it will change it for me. So I recompute, click, it changes. I click the platform weight button, it changes. Okay, now I can say OK. Okay, so now my model is updated with these new changes. So anytime I start a new model after this, everything will be in accordance with the default layout angle positions. Okay, so that was something that was interesting and fun for us to do. Okay, next. Of course, we always like to help out our community of engineering users by offering international standards. So in 2009, actually, in the build, we added the Venezuelan code, which was the PDVSA, and for 2010, we added the Chilean seismic code. So we can have a real quick look at that. Let's see. This is where you can see it. So if we go to the seismic codes right here, you'll see that the Chilean code is one of our new options. So basically, again, it's just going down and entering the parameters in that you need based on where the vessel goes. Okay, so again, we can have press the F1 key right here to get some help. Okay, and I'll show you that. So it tells us what all of these various input values are. So you can have a look at those. You know, if by chance you would rather read this in Espanol, you can simply click right here and have all of the inputs in Spanish. Okay, now I will tell you all right now that my Spanish is not that good. In fact, it's terrible. And my esteemed colleague, Mr. San Juan, was gracious enough to do this for us. Okay, so we have help in various, in at least 2 languages. And just another thing, the Australian codes were updated to their latest versions. And one other thing that we did here was that, speaking of languages, is we have also started having our output in different languages, and you can see the different choices here: English, Portuguese, Spanish, French, German, and Italian. So now bear in mind, this is only the input echo at this point. So if I say OK and I rerun this model, and I'll just do an error check right here. See, if I look at my my input echo, it didn't do what I wanted it to do. So, but anyway, so we do have other codes or other languages available for the output. Okay, let's see. And with that, I'm going to pass off the demonstration to my colleague, Chris Schiller. And Chris will be giving a brief presentation of PV Fabricator. I'd like to thank you all for taking your valuable time to listen to us, and have a great day.
Thank you, Scott. Chris, welcome.
Can everybody hear me? I sure hope so. Go ahead and show my screen. Okay. Can everybody see my screen? Yes, no? Elvira?
I can see it, yeah.
Okay, so everyone can see it. Okay, so what you should be seeing is our PV Fabricator program that was released a little less than a year ago in conjunction to connect it to PV Elite. Some of you may have already seen this in past webinars or different events that we've held throughout the world, or through me directly visiting your office. If this is your first time, or if you've seen it before, thank you again for your attention. What we wanted to do with Fabricator was design a drawing package to take a vessel that's already being analyzed and get it into more of a, the fabrication drawings a lot faster than what you've been doing. And we wanted to save time on, that process. We wanted to save time on errors and mistakes that can occur and often do occur between the engineer and designer. It's to no one's fault on either side, but just human error sometimes. We don't always maybe make the changes or the updates that the other person had mentioned we need to make on our side. And so what this PV Fabricator does, it runs on top of AutoCAD, and we've got a connection to PV Elite. And I'm just going to quickly show you that here. I'm not going to go into a lot of detail here today. I know we've had past webinars about this. And if you would like more information, you can always contact me here at COAID or go to our website and get some more information. So what we have is we have a Fabricator palette over here on the side. And all I simply want to do is click on this import button down here on the sort of bottom left of this palette. And then what I'm going to do is go and find the vessel that I've been working on, so I can bring that in to my current system. And it's just going to read the native PV Elite file. The nice thing about that is we don't have to convert any of this information to neutral files or, going to this type and to that type. It's just going to read a PV Elite file. Nice thing as well, from this program, I can export changes that I were to make from this back into a native PV Elite file. Okay, I've got a layout here. I'm going to go ahead and just get rid of this view. I've realized I don't need that. So I've got a view and a layout of sort of what I would like on just a general basis here. I'm going to go ahead and create a 2D outline, 2D representation. That way, as you can see real quick, I can come down here and I can get a nozzle schedule for this vessel that I've got built. I can also come over here and I can look at a complete bill of materials as well of these components that I've added from PV Elite. And of course I can go down the list and I can just verify that all of this information is correct. I've got a material, a length, and a thickness for each one of these. Okay. Now the next steps that we have here to take, for example, are going to be, well, what about tagging, dimensioning, adding maybe some details, and things like that. The order in which you proceed going forward is really up to you as a company, as an individual. We don't specify that order. We allow you to work in your current workflow that you have now. We allow you to work in that, continue to work that way. And the first step is that, as you saw before I brought that model, and I had a general layout of where I wanted my bill of material, nozzle schedule, design information, notes, and things in my title block. I had my views already in place. I can already have these set up, so I don't have to do this every single time I'm going to come and start just, creating these drawings. I can already have my settings in place for me. Quite simply, all I need to do is import a vessel, and then I can start utilizing the power of PV Fabricator. Okay, so from here, I'm going to maybe put on a few details. So maybe not that many. I'm just going to drag those I want to put in here. And I'm going to place these details where might be appropriate. Okay, and again, I can put as many details or whatever I want on here. Maybe I want to come over here and let's do some tags. Oops. Maybe some nozzle tags. Okay, so we'll pick a nozzle. Grab the snap. Okay, now we'll come here. Just grab these. I can pick whatever point I want to. I can tag my nozzles, okay, and I can keep doing that for the entire vessel that I wanted to. And maybe another thing I want to do is I want to come over here. Let's look at this top section, and let's do some bill of materials real quick. Grab this head. And I just need to start picking points, grabbing components. And I can tag the bill of material as well on all of these. And if I were to go over here to my bill of material, for example, I just saw the 1 was the head, 2 is that body flange, and 4 was the main cylinder. So I've got a link here. And then, of course, the last thing to go ahead and show is we can go ahead and look at dimensioning. Let's pick a start point that we want to dimension to. Go to that point there. We can just keep going and doing a few here. Let's see. Grab this other point. We'll throw that one there. Okay, so we can go ahead and throw on a few dimensions. And I could have kept in the same command and to continue to start dimension. And I can dimension to whatever I want. And we can see that I started it down here from this weld line of that head. Okay, and I can do all the components. I can only do some. Maybe I just want to do the nozzles. It's up to me. And I could go over here and dimension off of this one as well. Okay, and now a few last little things. Just as far as cleanup goes, maybe I want to turn my viewport, my lines off. Just using some plain and simple AutoCAD commands, and I can do that. Okay, so in a nutshell, sort of in a quick fashion, this is our PV Fabricator program. It allows the connection to go from PV Elite to Fabricator, to PV Fabricator. Also, we can see down here, here's the vessel that was brought in my model system here. Okay, and it looks like exactly how it was out of PV Elite. And just lastly, if I want to make changes, I can. I'm going to come over here to this. This is a 14-inch inlet. I'm going to change the size on this just for our purposes. I'll make it a 4-inch. Take the pad off. Apply. Okay. We can see, obvious on this left side here, this nozzle also got really small. I'm going to export that out. I'll throw it on my desktop. Okay. And now what I need to do is just go ahead and open up PV Elite. Okay, and then what I'll do is I'll go ahead and open up that back into PV Elite, and we'll be able to see these changes brought back into the model. Oh, 2009, and we're doing 2010. So I'm going to go ahead and close that real fast. I'm going to open up 2010, since that's what we're using here today. Bear with me just a second. Okay. So if we go to File, let's go Open. Grab that one off the desktop. We can see, there we go. We've got a small nozzle. I can verify it's 4 inches. The pad has been taken off. And, of course, because a change was made, I can use PV Elite to verify this nozzle has passed. And this one will pass based on these changes. So, and that can, like I say, go back and forth. On this one, the nozzle hasn't updated. I can quickly allow this function to update the 2D model. And now that nozzle on both sides has changed, and that tag will have to get reassociated with that nozzle up there. Okay, so this is the PV Fabricator program. Like I said at the beginning, if you have any questions, or if this is the first time or like more information, you can visit our website, or you can contact me here directly at COAID. So thank you very much.
Thank you, Chris. Unfortunately, we don't have much time for questions, but we will cover all the questions and we will post them on our blog. So you can always view and read all the questions asked in the PDF format file. It will be posted in a couple of days, as well as the video, this recorded video of this webinar will be posted as well. Let me give you that screen here. The recorded webinars will be posted in our blog, Insider blog. I'd like to mention also, if you still did not receive PV Elite 2010 version, please contact us at sales@coaid.com or call us. And I'd like to remind that we're going to have PV Elite training and seminar from March 8th to March 10th. You can always register online for it. Thank you very much for joining us today. And the recorded version, again, will be available together with all the questions asked. We also plan to have another PV Elite webinar sometime in March on heat exchangers. Thank you very much, and have a great week, guys. Bye.